I need to present part of my work for PhD and for the enzymatic degamine of crude wheat germ oil. The outline of the production hypothesis, objectives, and materials and method and result and conclusion. For the production, wheat germ is a byproduct from oil processing. It consists about 8 to 14% oil, and the germ conserves several essential nutrients like vitamin B, vitamin E, calcium, magnesium, folic acid, essential fatty acid, and phosphorus and minerals. For the chemical composition of the wheat germ oil is a good source of polyunsaturated fatty acid, and therefore a good source of alpha-tocopherol, trichlorol, and polyphenol. And for the wheat germ oil is dark in color and strong in order and flavor depending on the oxidation condition of the oil. And for the wheat germ oil is a number of nutritional and health benefits used as food additives, as an antioxidant, and therapy agent for pharmaceutical industry, and for the cosmetic formulation, and used as dietary supplement. For the use of refining oil, it's good take a seed, and after that preparation for the seed, and after that extraction with different kind of extraction, mechanical extraction, solvent extraction, or supercritical extraction to get the food oil. After we get the food oil, we need to refine this oil with different process, degaming, neutralization, bleaching, cauterization, and deodorization, and we are focused on the degaming process. The goal of refining is to remove the undesirable compound of the negative effect for the negative effect of the compound. And for wheat germ oil refining is a big challenge because we have a high content of polyunsaturated acid and other bioactive compound, and this bioactive compound is very sensitive to the light and the heat. And the phosphorus content of crude wheat germ oil can be minimized by degaming, which is the first step of refining to get the edible oil. And the degaming process can be degamed by water degaming, or using acid degaming, diluted acid, citric acid, or phosphoric acid, or by using enzyme. And degaming can be converted the phosphorus to the hydratable gum, and can be removed the gum by using centrifuge or filtration. For the enzymatic degaming process, using the enzyme to convert non-hydratable phospholipid to hydratable phospholipid, and utilize the enzyme enhanced to refine the oil yield by improving the release of the oil from the gum. For this figure, we can use the classified of the degaming for phospholipases A1, A2, or B, or C, or D, depending on the bound die attack for phospholipid molecule. And different phospholipases that can be used for degaming, like lactase ultra, lactase 10, lactase novo, and perfume, and Lysamax, and gumzymes. And for the, I use the lactase ultra and Lysamax and the gumzyme, and for the perfume is not commercial use for the people. For the problem statement, enzymatic degaming is the major vegetable for the vegetable oil has been studied, but for the wheat germ oil is not studied or looked until now. And for the enzymatic degaming, the enzymatic degaming is more efficiency than the other conversion method like water degaming and acid degaming to remove the phospholipid from the oil and get the high oil yield. And for the objective of this study, the main objective of this study is to optimize the enzymatic degaming process for crude wheat germ oil refining. Materials and method, we get the crude wheat germ oil from vitamin company, and this is the crude wheat germ oil has high phospholipid content, about 1,864 parts per million, and for the free fatty acid about 90%. And I use the three kind of enzyme with lactase ultra and Lysamax from Danisco, and gumzyme from DSM. I use for the inverted variable for the for the enzyme, the two kinds of enzyme, lactase alpha and lysomax, and for the enzyme concentration, 3 levels of enzyme concentration, and 3 levels of temperature, with 3 levels of time, and 3 levels with water to oil percentage. And I use for this study the fractional factorial design for this study. And I get the result. I need to compare the optimum condition for the different kind of degamming process. For the water degamming, I get the result of phosphorus content is 817 part per million, with the oil yield 92. And for the acid degamming with different kind of acid, citric acid or phosphoric acid, for the citric acid, I get the result for the phosphorus content is 1024, and for the oil yield is 29. And for the phosphoric acid, I get the result for the 989, and the oil yield is 93. For the enzymatic degamming, lactase alpha is more efficiency. For the use the phosphorus content is about 290, and the oil yield 88, and for the lysomax is 294 and the oil yield is 89. And I test for the optimum condition for the enzymes at 5. I get the result for the phosphorus content 564, and the oil yield is 90%. For statistical analysis, I test the enzyme and the temperature and the time and the concentration and the water to oil percentage, and the interaction between the time and water to oil percentage, and the interaction between time, the concentration, and the temperature time interaction. We get the significant effect of the time onto the water to oil percentage, and the significant effect for the time with concentration. And for the enzyme, I get the significant effect for the using enzyme. For the optimum condition at the 6 hour and a half, I get the result when I increase the concentration, decrease the phosphorus content, and I get the good result with the lactase alpha compared with the lysomax. We use as different kind of adding water to oil percent. For my conclusion, enzymatic degamming is more efficiency than the other conversion method to reduce the phosphorus content, and for the optimum condition, the phosphorus decreases from 1,864 to 2,290 by using the enzyme lactase alpha with the time 6 hours and a half, and the concentration of the enzyme 750, and the temperature at the temperature 60 degrees C. And the oil yield for the enzymatic process was about 89% to the optimum condition by using the lactase alpha. Thank you, sir.